now look at the applications there, how you calculate the decimal values. So let's first of all look at that number 2010, 2021, 2021. It's got a little 10 as a subscript there. When dealing with number bases, we normally would represent, or we want to specify which base we are using. So by default, we just normally use base 10, so we don't write the 10 there. Sometimes it's written as a 10, or you can just write it as a D to show that it's a denary or decimal. D or 10. That's the base is written as a subscript. So how does this work? In order to say if number is actually 2021, you take that number and subdivide it into its place values. And then each of those place values, the furthest to the right is in position 0. And then as you go further and further left, each of them increases by 1. The position increases by 1. So the one in position 0, what you simply do is you multiply the number in the position 0 by the base. In this particular case, our base is 10 to the power 0 because it's in the position 0. So that's how you get that 1 times 10 to the 0. Then the next number there is 2 times 10 to which position? It's in the position 1. So it's 2 times the base, which is 10 to the power 1. The third position is, we have a 0 there. So we have that 0 times 10, which is our base, to the power of 2 because it's in position 2. Finally, we have that digit there, which is a 2. Multiply it by the base, which is 10 times 10 to the power of the position, which is in position 3, 10 to the power 3. So once you do that, the next line shows the values that you get. You'll then have 2 times 10 to the 1000. 2 times 10 to the 3, which is 1000. So you have 2 times 1000 plus 0 times 100 plus 2 times 10. Remember, anything to the power 1 is that number itself. It remains 10. And anything to the power 0 is 1. So 1 times 10 to the power 0, which is 1 times 1. So you just add those numbers, and that is how you get the decimal equivalent of 2021 as 2021, because you're simply using base 10. Now if you're using that number 2021 having been represented as a base 8 number, and you're trying to find its decimal equivalent, what number would be equal in the decimal system or the denary system to a number written as 2021 in base 8? We apply the same principle where we're going to say we separate them by place value. In the first position, which is position 0, we find that 1 there. So we're going to say 1 times the base. This time the base is 8, it's not 10. We have 8 to the power 0. In the second position there, we have 2 times the base to the power 1, because it's in position now 1. The second position is 1, remember? So the base is 8 this time, it's not 10. In the third position there, it's 0 times 8 to the power 2, because it's in position 2, which is the third position, and the base is 8. And then the last one there is 2 times 8, which is the base in this particular case, times 10, so rather, times 8 to the power 3, because it's in position 3. You multiply those. 2 times 8 to the 3 is 512, plus 0 times 8 squared, which is 64, plus 2 times 8 to the power 1, which is 8 itself, plus 1 times 8 to the power 0. Remember, anything to the power 0 is 1. That's 1 times 1. And then we end up adding up those numbers, and we see that a number written as 2021 in base 8 has the same value as 1041 in our base 10, which is what we normally use. So for binary here, we'll notice that we don't have any 2s because it does not exist in the vocabulary of base 2. So we basically, this number has been changed now, the subject number, we're no longer using 2021, instead we've used 1011. You're not allowed to have the digit 2 in binary. So we apply the same logic there, whereby we're saying the one in the last position is a 1, so we're going to multiply that 1 by the base, which in our case here is 2 to the power 0. And then in the next position, position 1, we're going to multiply the number that exists there, which is 1. We're going to multiply it by 2, which is the base, to the power 1, which is the position. In the third position there, we find a 0. So that 0 we're going to multiply it by the base, which is a 2, to the power 2, which is the position. And then finally, we have a 1 in that position there. We're going to multiply it by the base, which is 2, to the power of the position, which is 3. When you add those up, we find we get 1 times 2 to the power 3, which is 8, plus 0 times 2 to the power 2, which is 4, plus 1 times 2 to the power 1, anything to the power of 1 is that thing itself, which means 2, and then plus 1 times 2 to the power 0, anything to the power 0 is 1, that means 1 times 1. We add those together, and we have our answer there as 11. So 1011 in base 2 basically represents 11. You see that we're actually using 4 digits that represent a 2-digit number, 11. In fact, even 9 in base 10, in base 2 is used. 1 is a single-digit number. In base 2, you'll be using 4 digits to represent just 9 and 8. And then finally, let's look at hex base 16. There we use those numbers 2021, and then in order to get that value there, I think we may have wanted another example. I'll put in another example on the slide show, which will be uploaded, where we have actual letters. We have letters there representing the base 16. So here we only have numerals, but we could also have it with letters. We use the same principle. The first position 0 there has got a 1, so you're going to multiply that 1 by the base, which is 16 there, to the power 0. And the next one is the 2. We're going to multiply that 2 there by the base, which is 16, to the power of the position, which is 1. We're going to multiply the third one there which is 0, by 16, our base, to the power of the position, which is 2. And then the last one there is a 2. We are going to multiply that 2 by the base, which is 16, to the power of the position 3. We end up having 2 times 16 to the power 3 there, which is 4096, plus 0 times what we have there, which is 16 squared, 256, plus 2 times 16 to the power 1, which is 16, plus 1 times 16 to the power 0, which is 0. We add those numbers up, 8,192 plus 0 plus 32 plus 1 to give you that number there, 8225 base 10, or 8,225 in base 10. Notice now how the number 8,225 is represented in base 16 using a significantly smaller appearing number. So which then tells us that you can use base 16 numbers to represent very big numbers, but using lesser appearing values, using lesser or fewer numerals, for instance. So this is one reason why I would favor using base 16, especially when you're going to be using or representing very large values. Okay, like I said, I will just add another one there. which will show us how to use base 16, but this time including letters, because let's say you have now C, or let me say 208C. So the C there would then be, instead of that 1 there, we would be having a C. So the C would be C times 16 to the power 0. Where C is what? You then have to find the decimal equivalent of C, which is, which is 12 rather. So you then have 12 times 16 to the power 0. You have that C. Okay, I think with that we have come to the end of the class. Like this video and subscribe to this channel for more such content.